Good morning to all. I am Dr. M.V. Dandapani from Meg Design Consultancy, Coimbatore. Today, I would like to share with you regarding the topic of validation. So, before going to explain about the validation part, let me explain what exactly the meaning of validation. Let's go to the video. Validation is the most important parameter for any core mechanical industry product development. Suppose, say for example, if you are going to manufacture any product, before going to manufacturing, first of all we should understand the purpose of a product or the concept of a product. And next is, once the concept is completed, then we will go for CAD modeling or something called 2D drafting. So once the CAD modeling is completed, then manufacturing will start. But manufacturing, before going to manufacturing, first we need to validate that particular product. So how we have to validate? Number one, we need to do the hand calculations or a mathematical calculations. By using that calculations, we have to determine stress or deformation and so on. There are many parameters are there. So in that value you can arrive from the predefined formulas or predefined mathematical equations. Let it be as it is. And another part will be the same model you are going to create a CAD model. Any CAD 3D CAD software you can use, either SolidWorks or CATIA or Creo, whatever it is. You can use these software and create the model. And those model you can import it into ANSYS software or any FEA softwares, which is also called as CAE softwares. So this software will give the complete solutions. Depends upon what type of load you are going to apply and what type of analysis you are going to taking care of that. So based on that result you can arrive the values, and now you can validate from the mathematical calculation result as well as in your FEM results. Both the results you have got it. Then based on that result you have analyzed whether both the results will be almost it is closeness to your accurate result or not. If you are getting almost your closeness result means, then that should be very, very excellent. Generally, in any mechanical industries, approximately 2 to 4% of plus or minus deviation will be accepted. Even some industries, we need a very, very high accuracies. Okay, once if you got those results, then what we have to do, whether everything will be fine, the results will be same, almost closeness to your accuracy means, then directly go for manufacturing or directly go for production of a product. Suppose the same product, what will happen? You are getting the higher value as compared to your mathematical calculated value, because mathematical calculated value almost it should be accurate results. So these results you are compared with your FEM results. If it is higher than this one, then this is over design. So what we have to do, we need to do the optimization. Optimization means the various parameters you have to change it, and you can get the final or accurate results closeness to your calculated value. Sometimes what will happen, the same results you are getting very, very less value as compared to your mathematical calculated value. In that case, definitely the product should fail. So to avoid that such type of failures, what we have to do, only thing is we have to do the modification of a product. So how we have to modify the product? Maybe the various parameters, which means size, like length or thickness or diameter or whatever it is. So it depends upon the shape and size of a product. You can modify it by using FEM softwares, by using CAD softwares. And again you have to do the such type of iterations, FEM iterations. Then finally you can get those values which is similar to your FEM, mathematical calculated value. Then definitely whatever the final shape and size you have arrived, that should be match with your mathematical calculation. Then what we have to do the 2D draftings, go for manufacturing, such a way that before going to manufacturing any product, we have to do the basic calculations and further we have to proceed for manufacturing. Okay, and let us take a simple example and you can understand very easily. Concepts like a stepped bar, which consists of 3 sections, section 1, 2 and 3. In the first section with the diameter of 20 mm and the length of 200 mm, and the second section we have 30 mm diameter and 250 mm length. Third section we have 50 mm diameter and 220 mm length. Both the ends we have the axial load like 35,000 Newton towards left direction and other one is towards right side direction. Our main objective is to determine what are the various axial stresses which is occurred in all the 3 sections, and also find out the total extension or elongation of the bar. Assume this is a structural steel material and the Young's modulus is 2.1 e power 5 Newton per millimeter square. So first what we have to do is, you can write the length and diameter here, and axial load is 35,000 Newton. Let us consider the first section. We know that like stress calculation by using the formula stress is equal to load by area. So here the stress is equal to P by A is the formula is used, and first we have to determine area A1. Assume it as the first section, A1 equal to pi by 4 into D1 square, and after simplification we have got A1 equal to 100 by millimeter square, and apply these values because already we know that the axial load is 35,000 Newton. So 35,000 Newton divided by 100 pi, finally we can get the stress value of 111.408 Newton per millimeter square. Similarly, for the second section, if we want to determine the stress value, which means sigma 2 equal to P by A2. So what we have to do is, again you have to calculate the second section, sigma 2 equal to P by A2. We know that the value of P is 35,000 Newton and the A2 is calculated by using the formula pi by 4 into T2 square. Finally we have got 225 pi, and stress values around 49.51 Newton per millimeter square. Again similarly for the third section, using the formula calculate area and substitute the value, then finally we have got sigma 3 is equal to 17.825 Newton per millimeter square. Therefore all the 3 sections we have stresses like sigma 1, sigma 2 and sigma 3 as shown here. And next is determine the extension of a bar or elongation of a bar. So we know that this Young's modulus equal to stress by strain. So by using the Young's modulus formula, we have to determine the extension of a bar or elongation of the bar, stepped bar. So how we have to calculate? You just see that Young's modulus equal to stress by strain. Stress is equal to P by A and strain is nothing but change in length by original length. After simplification, we have got elongation or change in length is equal to PL by AE. You just see here P by A into L by del L. If simplified, we can get this value PL by AE. Here the value of P, which means axial load is 35,000 is Newton, right? So it's constant, and also Young's modulus is also constant. So take it separately, and here we can get L by A. Therefore P by E into L by A, you just take it. So P value is 35,000 Newton and the Young's modulus equal to 2.1 e power 5 Newton per millimeter square. After that we have a 3 length and 3 area. So L1 by A1 plus L2 by A2 plus L3 by A3. So all the values we know that, substitute all the values, and finally we have got del L equal to 0.183 millimeter. So this is how we have to calculate the stress and extension of a bar, stepped bar. So this is how we have to calculate and finding out the stress value and the elongation of the bar, which means the total deformation. Okay, so now let us see that whatever the calculation we have just now completed, it is also called as like scientific approach by using mathematical calculation or hand calculation. Right. Now let us see that by using ANSYS software, how we have to calculate the same stresses and the total deformation or elongation of a bar, and how we can validate it. Okay, just minimize it, directly you can go with ANSYS software. Now let us discuss about ANSYS workbench. A simple example like stepped bar we have to consider with the dimensions as shown in the figure. So already we have calculated by using mathematical formulas. So the same values we have to arrive by using ANSYS workbench. Let us take the ANSYS workbench window. Here this analysis systems we have to consider ANSYS static structure analysis. You just double click on that and you can get the project scheme of this particular stepped bar, and this particular window which consists of the project which contains engineering data, which means material properties, geometry, model, setup and solutions and final results. So as per the FEM concepts, we have a three basic steps: pre-processing, solution and post-processing. In that pre-processing, which consists of engineering data, geometry, model and setup. Apart from this, the solution process is nothing but the sixth step, and the last one is post-processing, which means to see the results. Okay, let us take one by one. In engineering data, if you double click that, the complete material properties which will be considered for solving the stepped bar. The default static structural material was selected, and here we have to see that these are all the basic properties. Mainly we should consider for Young's modulus. In terms of Pascal, we can make it as megapascal. So the Young's modulus value is around 2.1 e power 5. So we can make it 2.1 e power 5, and Poisson's ratio 0.3. And here the yield strength of the material is the default value which is available 250, but we are going to consider the material is C07. In that C07 material, yield strength is 200 Newton per millimeter squared or 200 megapascal. So here also 200 megapascal we have to take. And the next part is once the material is defined properly, then we can go to the project window, and next is geometry. Directly you get right click and one more window will open, that new design modular geometry. So in this particular window, you are going to create the stepped bar by using the predefined features which is available in design modular, or otherwise you can make the geometry from any one of the 3D CAD software. After getting that, directly import it from the CAD model in terms of IGS file format or step file format. Then so that model will be getting from this particular window. Go to file, import external geometry, and here we have a stepped bar, and right click import. Then you will get this model. This is 3D CAD model, and these are all the features which is available in this particular CAD model. Again go to the project window. So these two steps will be completed. The next is model. Go to right click, one more window will open. So this particular window only you have to define. Already the material is defined, automatically this will be allocating. And meshing part, that is very important. We are going to use the predefined mesh. Once the mesh part is completed, then we are applying the boundary conditions or the loading conditions for solving the like FEM software. And yeah, this you can double click Okay, the model is opened. Here you can see that the project window, this is your geometry. In that geometry there is a model, and here you can see that assignment is the material. Structural steel already it's taken automatically because we defined already material. And mesh part, right click, generate mesh. We will get a mesh model. This is coarse mesh. Suppose if you want to make it a mesh, should be fine mesh, then we have to increase the number of nodes and element. Instead of coarse mesh, you can make it as fine mesh. Again go to the generate mesh. Yes, now we have got finer mesh. After that, static structural, there are some loading conditions. Before going to apply the loading condition, first we should understand the physics. Here what will happen, the tensile load which is acting on both the ends of the stepped bar. Suppose say for example you are going to apply 35,000 Newton on this particular surface. So in that, what we have to do is go to force, select the surface, and here you can make it the component. Already this is in the towards Z direction, so in that Z direction we can make it 35,000 Newton, and in the geometry selection apply, then the forces boundary condition applied here. Similarly for the opposite side, because the tensile load is applied on this particular stepped bar. And further again go to the force, select the surface. In terms of vector you can replace into components. Then this is negative Z direction, right? So here you can make it minus 35,000 Newton and select this. Then you have got, this is another boundary condition. No, so there are two forces is applied on this particular structure in terms of tensile load. So here what will happen, once if you can apply these two loads according to the equation of equilibrium conditions, we need one support for complete degree of freedom should be arrested. So what I am going to do is, any one of the like edge or a small point, we have to select and apply the fixed boundary condition, because there is no translation degrees of freedom and there is no rotation degrees of freedom on this particular point. So the tensile load means one load moving towards this direction and another will be in opposite direction automatically in one particular point. So that should be in fixed constraint. So in that condition only they have applied here. So the total boundary conditions, we can see that two forces and fixed support. Now I am going to solve this particular problem. It will take some few seconds. So creating the geometry, preparing the mathematical model, and once the mathematical model is converted, then it will be making solve, and after solving that write the load steps, and finally it will be results providing. And you can see that the solution, go to the stress, because we are going to see the stress on each and every section of the stepped bar. So equivalent stress, right click, evaluate the results, so you can get the results. You can see that, yes, one more important information, that unit should be converted into megapascal, and here you can see that there is the stepped bar results. Yeah, this is the result, and you can see that the total one measure stress is maximum is 114.86, and individually each and every section we wanted to check, like probe. I am going to select for the first section, each and every places the stress is 111.76, 111.82, 111.9, 111.8, 111.7, something like that. So now let us check with the theoretical value. So theoretical value of the first section we have got 111.408. By using FEA we have got around 111.7. 111.7. Okay, this is the FEA results. So here what I'm going to write is 111.7 is the stress for the first section. The next section, second one, again probe, select the second section, you have get the value of 49.55. Here the theoretical value is 49.51 and here also you will get it 49.55, right? Okay, and the next is the third section, stress value around 17.8 everywhere. So here the mathematically calculated the stress value 17.8 and from the FEM result also will get 17.8. Now if you check both the results, or you can validate this is the mathematical or theoretical calculation results and this is for FEM results. You can cross check with both the results. What will happen? Almost it's very closeness to your accurate results. So this is how we have to validate from the mathematical calculation to the FEM analysis results. Suppose in the particular FEM results may be higher than the theoretical value or lesser than the theoretical value. What will happen? If suppose we'll get a higher than the theoretical value, then we need to do the optimization on the stepped bar structure. If suppose you are getting the lesser value as compared to the theoretical value, we wanted to improve a strength and stiffness of that particular materials. Strength and stiffness of that particular materials. Okay, and in case generally the industry is expecting the what is the factor of safety of this particular structure, we have a formula like factor of safety which is yield stress by working stress. Okay, therefore here yield stress is 200 because already we defined it in the materials. In this engineering data we have already defined yield strength is 200 megapascal, right? This is getting from the design data book. Okay, and 200 divided by working stress. You can see that all the three stress values, this is 111.7 is the maximum stress or highest stress. So, or otherwise you can take this value also, no issue. Because as per the calculations, the largest value is 111.7 and from the FEM analyzer result we have got the highest stress is 114.86. Suppose if I am going to calculate the factor of safety, same value you can get it 114.8. Okay, so finally if you calculate, let us take calculator. Correct. Therefore the factor of safety yield stress is 200 divided by working stress 11.48. So this will get around 1.74. So roughly we'll get the value of 1.7. So this is the factor of safety. This is the factor of safety. Generally the factor of safety value we can get it always should be greater than 1. Any material, either if you go for a ductile material or if you go for a brittle material, the factor of safety should be greater than that should be safe design. So whatever we have done, it's a safe design. In case if you get the factor of safety is less, what will happen? We need to do the modification on the structure, maybe some changes. That changes is also you have to do depends upon the contour plot whatever we have arrived here, right? And this portion also. So depends upon the shape and size of the structure. Further we have to do analysis, then finally you will get the factor of safety should be greater than 1. Then only you get the safe design of that particular structure. Thank you.